Good morning. Welcome to the 38th lecture on economics, management and entrepreneurship. In our last lecture, we had started the discussion on capacity planning. There, we underlined the role forecasting plays in capacity planning, and then we said that there is a need to have three different types of forecasts. One, the most likely; two, the optimistic; and three, the pessimistic forecasts. And then we said that one has to go to the level of finding out the requirement of individual machines by considering plant efficiency and scrap factor. Then we said that once this is known, the problem then is to decide when and how much capacity to add. Now, if you recall, there would be different situations. We might like to order less amount at a particular year and get it every year, or we may have an alternative of ordering large amount, but obtain that at a later date beyond 1 year, maybe 2 years or even 3 years. Meanwhile, the company has the option of going for multi-shift operation or overtime or even subcontracting the work. Now, these options must be evaluated to find out what should be the quantum of capacity to be ordered and how much when it should arrive. Recall also that I had said that if we order for a larger capacity, most likely, since the investment is also quite considerable for larger capacity ordering, the investment requirement, the money required to get this capacity will be more. That means the fixed cost will be more, but the variable cost may be less. Under the same time, if higher amount of capacity is ordered, then there is a greater likelihood that the present capacity will fall short of the demand. Therefore, this excess demand must be met by going for overtime, multi-shift production or even subcontracting. Therefore, when this alternative of going for higher capacity is considered, the cash flow consideration for overtime, multi-shift operation or subcontracting must also be estimated, and these cash flows must be then converted into fixed cost or variable cost. Once for every such alternative, costs are estimated and costs are divided into two streams, namely fixed and variable. One can use break-even analysis that we had covered earlier to decide what should be the capacity that we should order. We will illustrate that with an example. Thereafter, we shall consider the case when the product may be in its introductory phase or in its major growth period, and therefore, there is an uncertainty with regard to the demand. Hence, this is a risky situation, and how to treat or how to take a decision under these risky situations. After we cover this, we shall take up a new topic today. We shall start a new topic, and that is plant location. But to start with, we shall continue with our capacity planning exercises. Here we have assumed that the demand for a particular product from 2013 through the year 2020 increase in this fashion from 2250 units per year to 4000 units per year. The unit price of the product is assumed to remain constant at 100 rupees per unit. Let us say that there are a few alternative plant sizes such as this. Annual capacity could be 2500, it could be 5000, it could be 10,000. So, there are three alternatives that we are looking for. The minimum size of the capacity that we may add is 2500 units per year, and the maximum capacity could be 10,000. The initial investment required for these three are estimated as 7 lakh, 12 lakh and 8 lakh rupees. As you know, the initial investment is then distributed on in its useful life period considering depreciation. Hence, the annual fixed cost will be much less. Assume that it is 25,000, 30,000 and 35,000. And as I had said, associated with these additions of new capacity, there are different variable costs and they have to be estimated. These details I am not discussing here. We have gone through a number of lectures on how to estimate the variable cost and the fixed cost. For example, in the variable cost we shall have labor cost, material cost, power cost, certain amount of transportation cost, etc. So, they are estimated to be 50 rupees per unit, 47 rupees per unit and 45 rupees per unit. If I consider the annual fixed cost as F and the unit variable cost as V and the price as P, then I can use the break-even analysis method to find the best plant size that the company should plan for, whether it should go for 2500 or 5000 or 10,000 units per year. For that, you can imagine a cash flow diagram of this sort. Capital P is the initial investment. Of course, we are not much concerned with capital P right now. We will make a break-even analysis, and in the break-even analysis, we already know that P minus V into the demand D, that is the revenue. The annual revenue minus the fixed cost F gives us the annual revenue, and from there the break-even. One can make similar economic evaluation of alternative capacity plans to consider the effect of overtime, multiple shifts and subcontracting. So, one can find out which is best. Now, let us consider, so long we had been considering situation of a product which is in its maturity phase, meaning that the demand fluctuations are not much and that they can be easily predicted. Whereas, if the product is in its introductory phase or in its major growth period, then the demand may not be very much predictable accurately. Hence, one has to go for most likely projections, optimistic projections and pessimistic projections, and also find out and also estimate the probability of their occurrence, meaning that whether the demand is most likely probably will be having a probability of little high compared to the optimistic projections and pessimistic projection probabilities that are less. So, that all these probabilities adding would give a value 1. Then make alternative capacity plans as we had done earlier and estimate the revenues and costs for each year for each capacity plan, this also as we had done earlier. Now, we find the expected value of each capacity plan and select the capacity plan that gives the highest expected value. This we shall illustrate with the help of an example. This is called a decision tree, and the approach taken here to evaluate and find the best alternative is known as a decision tree approach. Here you will see 3 types of symbols. One, a square symbol, a circle or ellipse symbol, and then certain lines. So, what we are showing here, this is called this ellipse or circle, it looks like an ellipse here, they are called chance nodes, and the square node is called a decision node. It says that we have 3 decisions to make or 1 decision to make out of 3 alternatives. One is we can go for capacity A, another alternative is capacity B, and another alternative is capacity C. So, we have 3 alternatives, and this is the place where we have to take a decision whether to go for this or this or this. Suppose we take capacity A, that means we order for capacity A, then there are 3 possibilities. These are governed by nature, these possibilities or probabilities are governed by nature. This is a random phenomenon. It may be optimistic scenario, the demand may be very good, the demand may be very bad, meaning it is pessimistic, or demand may be somewhere medium. So, therefore, this node is called a chance node governed by nature, whereas this is a decision to be taken by the management. Therefore, it is called a decision node, and these are chance nodes. Now, if the demand is optimistic, we assign now the probabilities. We say that most likely scenario is 0.5 probability and optimistic and pessimistic chance is 0.25 probability each. Now, if the demand is 0.25 and if we go for capacity plan A, then what are the cash flows and what is its present worth? I do not have to go for details of this. You have to make estimates of the revenues and the costs associated in future years, and then discount it to the present to find out the present worth of alternative A. Similarly, if the demand is most likely demand scenario that we had projected, its associated present worth can also be calculated for capacity plan A. And similarly, if the demand is pessimistic, then what is the present worth of all the cash flows associated with this demand projection. Once you know or you estimate the present worth associated with the 3 possibilities, then we can find out the expected value of present worth of capacity plan A. How we find out? We multiply this value, which is a numerical value, with 0.25, add to this product of 0.5 and PWA here calculated for the most likely demand scenario, plus the product of 0.25 into the present worth associated with this pessimistic scenario, and whatever we get, that is the value of expected value of the present worth of capacity plan A. Following a similar procedure, we find out the expected value of the present worth of capacity plan B, meaning you will have to make the present worth calculation for this demand scenario, and this demand scenario separately, and then 0.25 multiplied by this plus 0.5 multiplied by this plus 0.25 multiplied by this. Like this you find out this, and assuming that they are all positive, present worth is positive, meaning the revenues are greater than the cost, then this value is, these three are also positive. So, the best alternative to go for will be that particular plan for which the expected value is the highest. That means, find out that value, that capacity plan for which this is, these three, one of these three is maximum. I will give an example. Say here we take, this is the decision node, this is the chance node. Let us assume that this is 0.25 and this is 100. This is 0.5 and this is 80. This is 0.25 and this is 60. Then the expected value here is this into this is 25 plus this into this, which is 40, plus this into this, which is 30. That gives a value 95. So, the expected value of alternative A here is 95. Similarly, we calculate for B, let it be 85, and for C, let this be 100. So, the best alternative to go for will be go for C rather than A and B, the maximum of these three. That is what I am proposing. So, we have seen how to go for capacity planning for two types of situations, when the demand is more or less deterministic, and that is possible when the product is in its maturity phase. We have also seen how to use the decision tree approach when a product is in its major growth period or in its introduction phase. Now, we shall move to a new topic, and that is plant location. Now, plant location is a strategic decision. It has long term implications, because once a plant is fixed, many costs get fixed permanently. For example, if a plant is located near its raw material source, then the cost of transportation of the raw materials from the source to the factory is less. So, this cost will remain permanently less for many years. At the same time, if a plant is located far away from the market to which it subscribes, to which it supplies material, then the cost of transportation of finished products to the market is permanently high. So, you can see that plant location influences long term costs and is very important. There are large number of other factors that also influence a plant location decision. For example, the climate, the labor relationship, the power taxes, and of course, there are other factors. Now, we will consider how to consider these factors and how to finally decide which location is the best. There are quite a large number of approaches, but we shall not discuss all of them. We shall only consider the very basic question of locating a plant and how the decisions are taken, the very simple models. So, plant location. As I said, plant location decision is important. It requires huge investment and a decision that affects long term performance. It has been seen that the manufacturing cost and the distribution costs can vary by 10 to 20% purely by plant location decision. Now, there can be different types of location problems. An entrepreneur who starts a new plant, that is one type of a problem. But if the plant is already existing, the problem could be adding a new location when the company is thinking to expand its facilities because of higher demand existing in the market, or the company may be deciding to close down an existing plant because of various contingencies and would like to start a new plant in a new location. The question is where to locate. The first thing that one considers in deciding a location is to enumerate the factors. There are different ways in which factors can be categorized. We have categorized factors in one way here, and that is factors that are input oriented, factors that are output oriented, and miscellaneous factors. There are other classifications that are available, but let us see this classification. Input oriented location factors. One, as I was telling you, proximity to input sources, availability of skilled labor, availability of power and water. You can see this is material, this is labor, this is power, water, availability of land and other infrastructural facilities. For example, IT services, banking services, transportation services, they all come here. And it could also be market oriented, principally whether it is close to the market to which it serves, and of course, other transportation facilities to carry goods, and of course, there can be other things like dealers, availability of dealers, networking facilities, etc. In addition to these two, there is a third type of factor which may be large in number, but only 3 are cited here: the business climate, political social environment, union activities, taxes and tariffs, and things like that. So, you can see that location factors can be many. The question is how to evaluate these factors and use them to decide which location is the preferred location. Now, the general procedure for tackling a plant location problem consists of 4 steps. Set the criteria to evaluate location alternative. What the criterion? What are the criteria we are going to use? Identify the important factors. Develop location alternatives. First decide which region, then decide what are the locations in those regions or that region, and finally evaluate these candidate locations and decide. Another type of classification of factor which is usually used when we go for evaluating the location is that a factor can be a critical factor or an objective factor or a subjective factor. Now, a critical factor is one without which the plant will suffer immensely. For example, an aluminum plant, the requirement is high amount of power. So, if power source is not available, aluminum plant cannot exist there. It is a critical input or critical factor for setting up of an aluminum plant. So, one has to consider the nature of the product or service that the business would like to give, and what is the most important factor without which the plant will suffer greatly. That is considered the critical factor. Then there are factors that can be evaluated in monetary terms easily. For example, labor, raw material, taxes, power and things like that. They can be evaluated in monetary terms. And subjective factors are those that are difficult to evaluate in monetary terms, and therefore, qualitatively they are measured, such as union activities, how strong is the union activities, industrial environment, whether it is conducive, whether there are many other industries already existing, so on and so forth. Now, a subjective factor or an objective factor could also be critical. Hence, critical, we say that if a factor is critical, then there must be enough amount of that factor available in that location for that location to be considered as a candidate location. If the amount of that factor, which is a bare minimum for setting up of the plant, is not available in a location, then that particular location should not be considered as a candidate location. That is how critical factor is decided. Now, we suggest a general location model. What it does in this model is first to define factors as critical, objective and subjective. Already we have defined what they mean. Then make a list of candidate sites. Then the 3 sets of factors separately find out their weights or measures. First, the critical factor. The measure of each critical factor for a site I is either 1 or 0. CFMI is critical factor measure for site I. It is either 1 or 0. 1 if the site I has an adequate amount of the factor, else it is 0. This is how the critical factor measure is defined. So, one has to subjectively decide whether the amount of that factor is adequate to carry out operations of the plant in that site. If it is less than adequate, then it is 0. If it is adequate or quite adequate, then it is 1. If a critical factor measure for the site is 0, then that site is excluded from consideration. Then the weighted average of objective and the subjective factor measures is multiplied with this critical factor measure for site evaluation. Now, let us find out how this weighted average of objective and subjective factor measures is calculated. First, the objective factor measures. There are two steps. Find the cost of each objective factor for a site I and sum them to find the objective factor cost OFCI. That means, for every site I, find out the value of each objective factor, add them up. The sum is the objective factor cost for that site I, OFCI. Then use this formula to find out objective factor measure for the site I. Here we have taken inverse -1 inverse. The reciprocal converts relative costs into relative profit measures. So, OFCI is the cost associated with the objective factor cost associated with site I, and multiplied this and inversion of that. We give an example here. Let us say that there are two sites A and B, and let us say that we are considering only 3 objective factors that are considered, that are possible to be measured objectively by monetary terms. Let us say that these are figures per rupees per unit, material cost in terms of rupees per unit, labor cost per rupees per unit, power cost rupees per unit. For site A, estimate says that these costs add up to 175 rupees per unit, and for site B, material costs 125, labor cost 40, power cost 35, and this is 200 rupees per unit. Then according to that formula, we find out the relative cost, invert it to find out the objective factor measure for each site A and B. For example, for site A, it is 175 multiplied by 1 divided by 175 plus 1 divided by 200 to the power -1, and this is this, which is 0.533. This is how this objective factor measure is calculated for site A, and for site B we calculate 0.467 in the similar fashion. So, this is how the objective factor costs, these are objective factor costs, and the objective factor measure, these two are the objective factor measures, are calculated. Now, go for the subjective factor measures. Here there are 3 steps. Estimate the relative weight of each subjective factor k, call it SFWK, subjective factor weight. Estimate the importance of each subjective factor k for each site, call it SWIK. The weights are normalized so that they add up to 1, and then find out the subjective factor measure SFMI, which is basically a weighted average. Now, weighted sum. I have given an example to illustrate how to find out the subjective factor weights and the subjective factor measures for sites. Assume that we have 2 sites, 2 candidate sites A and B, and we have 3 subjective factors, let us say water supply, climate, labor relation. Let us assume that for our business we consider water supply, these are the importance weight of factor. We are assuming that water supply, these weights add up to 1, as you can see. So, they have been normalized. So, this is 0.5, we give an importance weight of 0.5 to water supply, 0.2 to climate and 0.3 to labor relation. Then we say we consider site A. For site A, the water supply position is in a scale of 0 to 1, it is quite good compared to site B. So, this is 0.8 and this is 0.2. So far as climate is concerned, site B however is better, a shade better, 0.6, site A is 0.4, whereas both sites are considered equally good or equally bad in terms of level relation. Now that we have attached some values, that means we have evaluated site A for water supply, site A and B, and both sites we have evaluated for climate and for level relation, and each of these factors is given a weight such as this. We can now find out the weighted sum. For site A, the weighted sum is 0.63, which has come by multiplying 0.5 with 0.8, adding 0.2, product of 0.2 and 0.4, and then once again adding the product of 0.3 and 0.5. 0.5 into 0.8 plus 0.2 into 0.4 plus 0.3 into 0.5, and that is equal to 0.63, and in a similar fashion this can be found to be 0.37, and as you can see these two add up to 1. This is the subjective factor measure for site A and site B. So, this is an example of how to go for calculate subjective factor weights and subjective factor measures. Now that we have found out the subjective factor measure, objective factor measures and the critical factor measure, we can find out a grand model. We can now make a grand model, we can call it a location measure for site I. Here within the bracket we have put x times the objective factor measure for site I plus y minus x into SFM I, meaning that we give certain weightage to objective factor measure and 1 minus that weightage to SFM subjective factor. We can give 0.4 40% weight here and 60% weight here, or we can give 80% weight here and 20% weight here. This again we can decide, and this is multiplied by critical factor measure. Remember that CFM can take only value 0 or 1. If it is 0, the location measure is not considered at all. So, we will consider only the value of CFM I as equal to 1. Here the value of x can change to find out how sensitive the location measure is for different weights that we assign to the objective factors and to the subjective factors. X is between 0 and 1. The site whose location measure is the highest is selected, or if it is that we are only considering cost and not profit, then the site whose location measure is the lowest is selected. Now, one can use a break-even analysis for site selection. Just as we had told for capacity planning, total cost associated with a production at a site depends on fixed cost, variable cost and volume of production. Fixed cost and variable costs vary due to location of a site. The site that minimizes the total cost for a desired volume of output is the best site. This is another approach for site location. This is an example. Consider 3 candidate sites A, B and C with the following costs. Suppose that we have estimated the fixed costs and the variable costs associated with location A, B and C in this fashion. Then we can find out the range of outputs for which each site is the best choice. This is shown here. This is the total cost for A, this is the green line, this is the yellow line A, and for B it is this, the lower value of a fixed cost and the higher variable cost, and C is the high fixed cost and low variable cost. Now, we can see that between A and B the break-even point is here, and between A and C the break-even point is here. Considering this, we can say that use B in this region, that means B is best if your volume of production is less than 50,000, C is best if your volume of production is 200,000 or more, and in between you go for A. That means, if your volume of production is between 50,000 and 200,000, then go for site A. Each site is the best for the volume of output shown below. A is good between 0 to 50,000, B between 50,000 to 200,000, C greater than 200,000 units. Now, at the end we take up a problem of multi-plant location. This is the case of a business that already has 2 plants in 2 different locations, and it is supplying its output to different markets, but it is finding that the demand has gone up, and therefore, it is deciding to set up another plant in certain location. I am illustrating this with the help of an example. Now, look at this. Here I am assuming that there are already 2 plants, plant A and plant B, and there are 4 markets P, Q, R and S, like North India, South India, East India, West India. So, market P, Q, R and S. Now, plant A has a capacity of 100 units per year. It can supply 100 units per year. Plant B can supply 200 units per year. It could be a year or it could be a month. And the demand from market AP, the demand of market P is 80, of Q is 90, of market R is 60 and market S is 40 units per year. So, the total demand is coming to 270 units per year. Oh, I am sorry, this is 100. This is 100. So, the total supply is 100 plus 100 plus 70 is 270, 100 and 100, 200, and the demand is actually 270. So, the present 2 plants are unable to supply the 70 units that are demanded by various markets. Therefore, the company is thinking to go to either site X or to site B. This is the next one. Here also there is a mistake, it should be 100. So, this is site X and this is site Y. The same thing we have written with site Y. Now, what are these other things? These are the things, this is the cost of production and transportation. Plant A can supply to market P or Q or R or S or to any other combination. Now, if I consider production cost, that is fixed, but the transportation cost differs. That will depend on the distance from plant A to each of these markets. Therefore, the transportation cost and the production cost together will be different for different plant market combination. Here we are saying that if I transport 1 unit of product from plant A to market P, then the cost of production and transportation comes to 25 rupees. Plant A to market Q, it is 35 rupees per unit. Plant A to market R, it is 45. Plant A to market S, it is 40. And similarly, we can find out the actual values. Now, if we go for new site X and if this 270 has to be satisfied, the demand of 270 has to be satisfied, then new site X must have a capacity of 70. And the production cost and the transportation cost together for every for new site X and market P could be 45. This is estimated as 45, 55, 25 and 65. Now, the corresponding figures for market Y are different. The corresponding figures for plant this row and this row, the entries are the same, but for the new site Y, the values are different. For example, they were 45, 55, 25, 65 and now it is 45, no, they should be, I have not changed this, actually they have to be changed, 45, 55, 25, 65 and this could be anything else, but not exactly the same. It could be 40, 50, 45 or 35 and 85. Now, you see from the new site X to market P 45, 55, 25 and 65, whereas now it is 40, 50, 35 and 85, they are different. But the capacity of the new site, it can supply 70, such that the total demand, which is 270, is equal to the supply, total supply 270. Now, this is fondly known as a transportation problem in linear programming. We can actually find out which plant should supply how much material to which market, so that the cost of production and transportation becomes the minimum. We are not discussing a linear programming problem or a transportation problem, but we are merely mentioning that this has the structure of minimizing the transportation cost, where the decision variable is how much to supply from plant A to market P, from plant A to market Q, R and S, similarly how much from B to PQRS, and similarly from how much from Y to PQRS, provided we go for Y, and in a similar fashion we can also find the same values for A, B and X. Find out, so that of course, so that the total demand in each market is satisfied and the total production in plant A, B and X is supplied to the markets. Now, we can find out the total cost of production and transportation if new site X is there, and in a similar fashion we can find out the total cost of production and distribution if new site Y is decided. Now, suppose site X is selected, then the minimum cost of production and transportation could be 5,500 rupees per year, and for site Y the minimum cost could be 5,000 rupees per year. It means select site Y. So, friends, in our discussion on plant location, we basically said that there are various factors that influence plant location decision. They can be classified in various ways. A convenient way of classifying is to classify them as critical, without which, or if the factor is not adequate, if such a critical factor is not adequate for a particular site, that site must not be considered further. It should carry a measure of 0. Then the other remaining factors can be classified as either objective or subjective. We must find out a measure for all the objective factors for every site I. Similarly, we must also find out a measure for subjective factors for each site I, and then we can find out a location measure for each site I, the one that gives the minimum if it is a cost criterion or a maximum if it is a profit criterion to select which location is to be used. This is a general location model. But if the factors can be subjectively, or I am sorry, if these factors can be objectively evaluated in terms of fixed cost and variable cost, we can use also a break-even analysis to find out which site should be selected if the production capacity is estimated. And then finally, we discussed a method of multi-plant location, where a company may be already having a few locations, a few plants. It is deciding to go for another plant and is thinking of which site to select. So, there we said that the criterion should be minimizing the total cost of production and distribution or transportation. There are various other situations of where to how to select sites. We are not discussing them any further. In our next class, we shall consider designing production system. In that, we shall talk about different product service strategy, and we will then talk about layout decisions, and thereafter we shall take up many other functional problems such as production planning and inventory control planning. Thank you very much.